What we did up till now, from lecture 1 to lecture 5, we covered basic information you need to be aware of from the literature of psychology and physiology in order to start thinking about what is a good criteria to adopt when designing a user interface. So all the information has been communicated to you as takeaways, which you could list from takeaway number 1 all the way to the last takeaway we have seen in lecture 5, which I think was takeaway 47, I believe. And these takeaways together will help you a lot in designing a user interface. Now, starting from today, we're going to be talking about design. The first thing I would like to cover in the design part, or the design component of the course, is I would like to discuss with you the different interaction styles that has been developed from the early days of computers up till today. And I'm doing that for a number of reasons. I want you to break away from the traditional desktop interfaces that you are most accustomed to. All of us grew up with Windows or Mac. And when we think of an interface, we are thinking of Windows or Mac. And if you actually reflect on the interfaces we build online for all kinds of websites, it is more or less trying to mimic what exists on Windows or Mac, with obviously the limitations set by the web technologies like HTTP and JavaScript and CSS. The final outcome obviously is a little bit simpler than what you see on the desktop. But what cannot be denied is that we are always having at the back of our minds when we talk about an interface, a desktop interface. You have windows, you have menus, you have buttons, you have scroll bars, and so on. Now, it is actually quite beneficial from an SI point of view, especially for the purpose of your project, that you think outside the box and stop thinking about desktop interfaces. And that's why I would like to go with you through all the interaction styles we have and discuss each one of them and where it will be used or how it will be used or how would you go about it. So you know the options that are available out there apart from the desktop interfaces. And I'm going to also cover desktop interfaces in my discussion, but just as one of the interaction styles. So perhaps I should start as well by saying, okay, or posing the question, what is an interaction style? Now, we have the digital world on one side and the human on the other side. The digital machines, like basically the computer, does not mean a screen, does not mean a mouse, does not mean a keyboard. It means a processing capability and some storage capability. A processing capability, I mean a CPU or a quad core, whatever, and a storage capability, I mean the hard disk. Every way of interacting with this digital world, we are calling it in SCI a style. And so the desktop environment, the Windows OS or the Mac OS, is just one interaction style, as we will see. But we have many, many interaction styles, way more than what you expect. So let's start seeing them one by one. So historically, the first interaction style that was created was the conversational interaction style. It followed this metaphor that humans converse with each other, they talk to each other, using a dialogue, using a language. And so the early computers all were built around this idea that I'm going to talk to the computer by typing in commands, which is the language that the operating system designer designed for me to use the computer. And what that meant is the user needed to learn the language of the computer. Just like you have to learn Deutsch if you're going to go to Germany and study there or live there, or you have to learn French if you're going to go to France, or you have to learn Japanese if you're going to go and stay and settle in Japan. you have to learn the computer language in order to talk to it. Okay? Now, for geeks, for software developers, for systems engineers, that was a very cool idea because the computer has its own language and they are more than capable of learning that. But for all other users, that was not really a good option, because if I want my grandmother or my grandfather to learn how to use a computer, and then I ask her or him or her, you gotta learn these commands and you gotta type them in. You gotta type something like ls minus xva, or you gotta understand how do you pipe from one file to another, okay? Or you have to understand the notion of a process, okay? Now, so you can type ps minus aux on a Linux terminal. Obviously, that's not very convenient for the user, okay? So the first conversation style was mimicking human-to-human dialogue, but in the computer language. It was quite limited because the language itself is limited, and it's all full of technical jargon that is not really a common knowledge between humans, okay? So for example, a command like ps minus aux, you gotta know Unix to understand what is ps minus aux, okay? But that's not something we talk about in English or in Arabic or in any language. Now, the conversational style was important because it showed that there are interfaces that are really bad to work with, and that was one example. And the conversational style led to the born of what we call the direct manipulation interaction style. Now, the direct manipulation interaction style is actually what you do when you work with a windowing system that is based on the desktop metaphor. And I have described that in detail when I was discussing the cognitive aspects of the human, that using metaphors invokes the proper conceptual model, and consequently we achieve zero learnability and so on. Okay? Now, the direct manipulation as an idea is actually coming from the physical life. If you look around, we're always manipulating things directly, which means if I would like to throw a piece of paper in the trash, I'm going to grab it and throw it in the trash. That's direct manipulation, okay? If I would like to write a letter, I will grab a paper and a pen and I will write the letter. I'm directly manipulating the pen to express my ideas. And this is what this interaction style is about, okay? Now if you go to the desktop environment, which is, where direct manipulation is adopted, everything you do on the desktop involves some level of direct manipulation. Even if you open an editor like the one in front of you, and I have here an old screenshot of an editor on Mac. This blue region that gets highlighted when you select some words is direct manipulation, because if you would like to delete several words, you highlight them with blue, not red, with blue, and then you press the letter delete on the keyboard and you delete them, so you directly manipulated it. Now, what are the other alternative here that could have existed is that you type in the conversational style, so prior to direct manipulation, what you would do is you type the line number that you would like to delete. Okay, there are editors in which this is actually supported, and some people still use this stuff up till today, which is, I believe, is quite inconvenient. So you say, you open an editor and then you go like delete, and then you count the line numbers or display the line numbers on the side, so you know which line number. You say delete 5, so that means delete line number 5. While over here you're directly manipulating the words, and then afterwards you delete it by pressing delete. Now, all of the desktop is based around the notion of direct manipulation. If you would like to organize folders, you grab the folders or you drag them, you put a folder inside a folder. That's exactly what you do on a real desktop. You put a folder inside a folder. If you'd like to delete a file, you drag the file to the trash bin, and it goes like this. So it's a metaphorical approach. I've discussed metaphors before. Metaphors is not the real thing, it's just symbolic representation of it that alludes to it from the shape, from the texture, from the look, from the geometric properties, but it's not the thing, and it doesn't have to be one-to-one mapping. It doesn't have to look exactly like a folder. You get the idea that it is a folder by just looking at it, but you know it's not exactly like a folder, okay? So this is the metaphoric usage, and my metaphoric usage is used, you know, to create objects that look like the actual objects in real life, and we apply direct manipulations on those objects to actually invoke the functionality. You know, you have to realize here that you know the whole desktop interface, whether it's Windows or Mac, it's all fake. You know, inside the computer on the hard disk, there is nothing that looks like the file icon displays to you, or that looks like the folder icon that is displayed to you. You know, there's no physical thing that looks like this on the disk. It's just a visual representation of binary content that's made up of ones and zeros on disk. But we make it this way. We kind of turn it into visual objects that have the look and feel of something that we know in the real life. So we are doing in the metaphor here, so that we can later on directly manipulate it, just like we manipulate the actual thing in real life. Now, the current interfaces, by the way, which has been around for many years, I've told you the story of XeroXPARC in another lecture, and it has been labeled, you know, WIMP interfaces, which stands for Windows Icons Menus Protocol. Okay, that's the historical name behind it. That I believe comes from XeroXPARC, but it has been imitated so many times that it's now how we think of computers. For example, this was the imitation that Steve Jobs did in, I believe, the Apple Macintosh, which was a very successful product by Apple many years back. And if you check this image against the image I was showing you from XeroXPARC, they're almost, you know, I would say it's quite similar, at least here. I'm not showing you all details here of the interface. It's quite similar to the XeroXPARC product. And both of them are classified as WIMP interfaces. Both of them support direct manipulation. Now, let's go back to this notion of the cues that invites you to directly manipulate an object. We already talked about this, so I'm stressing the point again. There are a number of properties, so I'm going to just expand as well on this a bit. There is a number of properties that has to exist in the visual object you're displaying on the screen to be able to do direct manipulation. The first one we've covered before. This is the infamous teapot, you know, the Chinese green tea teapot, because I like green tea, okay? Now, the affordness cannot be missed. You know how to, as I mentioned before, how to hold it and where the water is going to come out, versus the one on the right, which has no affordness. But this is not the only cue for direct manipulation. I will talk to you now about other ones. Okay? Again, this is an example we've seen before. This is the push and pull. I hope now you remember this stuff. You know, one of them has good affordness, the other one does not have good affordness. Or is it? Yes. Okay, if you remember, you know, at least I know now you're following, if you're following what I'm saying. I'm not sure because this is a one-way video. If you look on the left, it says, doesn't say, but what is this made for? You put your hand inside the inlet, and you only do that if you would like to pull it. Now, on the right side, it says push. Okay? So push, you usually rest your hand and then move your hand forward to push. So the handle is wrong affordness that appears on the right image. On the left image, the inlet where you put your finger in or fingers in, the affordness here is for pulling. Okay, so you don't even need a label here, by the way. That's why there is no label on the left image, because the only way you can work this is actually, or you can open the door, is you put your fingers or your hand inside the inlet and you pull it towards you. Okay, that's why they have the inlet. This is the right affordness. That's on the left. On the right is absolute disaster because it says push and it's give you a handle, and the handle is going to invite you to actually pull. Okay, so I think I covered this before, so I'm not going to spend any more time. Now let's look at another cue that also supports direct manipulation. This is called natural mapping. If I tell you, look at these two designs for stove and the control knobs that open and closes each one of the outlets. Now, which of the two has what I call natural mapping? Without reading the text at the top, which one do you understand it maps to the right outlet? Obviously, it's going to be the figure on the left. The figure on the left has 4 outlets and 4 knobs organized in the same layout. So you can map each knob to the right outlet. Now on the right, which is actually what we have on today's stoves, there is a chance you can get confused. In fact, every day in the morning when I make my green tea, I always get confused about which one opens which outlet. I usually make it on the right bottom outlet, and I will get confused between the two knobs at the right side, the two to the right, because there is no natural mapping in the right figure and there is natural mapping in the left figure. Okay? Now, natural mapping is important because it provides a cue for the user what to do, just like here with the stove example. Now, the third cue is visibility. Now, that the relevant parts of the system should be visible. Okay? In the real world, visibility is almost guaranteed because of the nature of things. Now, in the software world, the system is running on the CPU, or the software is running on the CPU. The interface is all fake. So unless the designer takes into account the visibility, there is really nothing that tells the user what's going on. Okay? Because what the user is looking at is the screen. The screen is not running the software. The CPU is running the software. Okay? So it is very important that whatever the user does, the effect of his changes are visible to him, and the status of the system is visible to him. Okay? What that means is anything that happens that the user needs to be made aware of, he should be made aware of right away. Related to that is this notion of feedback, that the only way the user will be engaged in a direct manipulation activity if whatever he's doing, he is seeing feedback that makes sense according to his real world or physical world experience. For example, in the real world, if I would like to throw a piece of paper, I grab it and I, take it in air in my hand and put it in the trash can. To reproduce this same behavior inside the computer, when the user is dragging a file or a folder to the trash can, it should be visible to him during the movement. So he sees that it's actually moving from its location and going towards the trash can, so that when it's on the top of the trash can, he can release the mouse. So visibility and feedback comes very close to each other. They come hand in hand. If you support visibility, you must provide feedback. If you provide feedback, you must support visibility. Now, those are the 4 cues of direct manipulation that exist on any user interface that would like to support direct manipulation, because they facilitate this interaction style. Now, let me show you one research work that takes direct manipulation in an extreme way, but it's a very entertaining and very amusing way as well. So this was a master's topic in a university in Canada, and the outcome of this master's topic is this product called PumpTop that the student has later on changed to a company, and actually the company was acquired by Google for an undisclosed sum. The idea is very appealing, and it works like this. The student developed a physics-based engine and created a 3D desktop using the physics rules to throw around and collect and group and sort through and search the different items that exist on the desktop. So what you're looking at here is a picture of his interface. This is his desktop, okay? Everything takes 3D shape. Everything is manipulated using physics, so it looks quite natural. When you throw something away, it hits the ground with the same movement you would see when you throw something on the ground. And when you sort through the items and when you pile them or unpile them, as he described them in the video, it looks extremely natural because it's applying physics rules to the 3D objects displayed in the scene. Okay, this is also an example of direct manipulation, but it's taking direct manipulation in a direction that has not been seen before. Now the third interaction style, which you are all familiar with by now since you have cell phones, is called gesture-based interaction. Now in this interaction style, we interact with the digital world using gestures, not using direct manipulation. So the gestures could be in air, which means it's going to be 3D, in 3D gestures. I could move my hand in any way in 3D space. It could be 2D, so I could make the gesture on a surface, or it could be even done using a pen or any drawing surface, like Microsoft Surface. Okay, so any device where I make gestures, not clicking with the mouse, but just gestures, we consider it as a different interaction style. Okay. Nowadays, this shouldn't really be new to you. You must have heard or seen or do have at home a Microsoft Kinect or an Xbox or something like any other device that works in the same way, like the Sony Wii and so on. Now, you use these devices to make gestures in 2D space or 3D space. Okay. Now, there's one important point here. The interaction styles are not mutually exclusive. In the same system, you could have more than one interaction style. Based on the context, you would use one interaction style more than the other, or you could use all of them. So this is not really a mutually exclusive solution to working with the digital world. They kind of complement each other in certain aspects, and they replace each other in other aspects. Okay, so gesture-based interaction, for example, exists on cell phones. When you navigate on a map, you are doing a gesture to zoom in and zoom out from a map. Okay, but also in a cell phone interface, you have direct manipulation. When you would like to uninstall a program, you select it by tapping on it, and then you drag it to the uninstall icon if you have an Android, to the uninstall icon on the top, which is direct manipulation. You're directly manipulating the program to uninstall it. So you see, you have gesture-based interaction, and you also have direct manipulation interaction. Now here is an example of taking gestures in a completely different, kind of unexpected way. What the researchers here were trying to solve is the problem of working with smartwatches. Smartwatches are really, really challenging, and as much as they sound like a cool idea, they're actually quite a miserable idea in certain aspects. The misery comes from the screen real estate size. The screen is incredibly small. It's too small to do actually anything. If you actually have a smartwatch, if you put your finger on the smartwatch, you can hardly see anything else left. So what the researchers here are doing, they mounted a magnet on the finger of the user or the researcher here, which you see on the right of the image, and they added to the smartwatch a magnetic field sensor. The magnetic field sensor detects changes in the magnetic flux around the watch because of the proximity of the magnet that exists there. So once the magnet starts moving, I mean the magnet mounted on the finger of the user. So basically, once the finger of the user starts moving, the changes in the magnetic flux will tell the magnetic sensor attached to the watch where is that in 3D space, where is the magnet in 3D space. Now once that is known, this becomes almost like a pointing device. So if you would like to scroll through the list, you can make a gesture to scroll through the list. So what the software is doing that is attached to the watch or installed on the watch is detect the gesture in 3D space. Whether the user is tapping, double tapping, moving around the watch, rotating in anti-clockwise around the watch or in clockwise around the watch, and from there you start driving the interaction. And you can see the video to see an example of using gestures in research to solve a problem. Now, the fourth interaction style is called multimodal interaction. Now, in the multimodal interaction way of thinking, you're going to use more than one modality to derive the interaction with a computer system. By modality, we mean speech, or touch, or pointing. So what you see here in this very classical work that introduced multimodal interaction, or invented multimodal interaction if you like, it's called Put That There, very popular in the history of HCI. As you see, it's made in 1980. Everything in the image tells you it's very old. The way it works is this system detects the pointing direction. So it detects the finger where the user is pointing, and it also detects the user voice. And actually the user here, I believe his name is John Bolt, if I remember correctly, was doing an amazing kind of interaction that up till today we cannot find a system that is actually doing what he is proposing here. So he would go like, put that there, move that from this location and add it to this location, delete this guy, make this guy red, and he goes like as if he's actually talking to his private secretary, pointing out, okay, do this, do that, do this, do that. Okay. Now he's using two modalities. He's using his voice commands, speech, and pointing. Okay. Now, as long as you use more than one input channel, input here, you're inputting information into the computer. So as long as you use more than one input channel, in this case it was the computer camera to capture where is he pointing, and the computer microphone to capture what he is saying. As long as you use more than one input channel, it will be called multimodal interaction. So you could use 3 or 4 or 5 depending on what you're really doing, but obviously that will make it more challenging. So watch the video. It's very entertaining. It's very old, but extremely creative. And if you think this was done 40 years ago, that tells you something. Now here is a more recent work, just that you don't get depressed, okay? so this is called Gaze Plus Touch from Microsoft, trying to solve the problem of working with tablets. Now the problem with tablets is that you hold them with one hand, and that means that your other hand is not really is the only one that is free to do any work on the tablet, because the other hand, the first hand, is busy carrying the tablet. So what they do is they use gaze, which is using your eyes, plus touch to do the selection of any item. So you look anywhere and you just dwell with your eyes, and the cursor will be there. And then you touch anywhere. You don't have to touch where the cursor is. And you touch anywhere after the gaze, then that will initiate the selection. So watch the video. This is another example, more modern example of multimodal interaction. Multimodal interaction is very interesting when it solves the problem, because it just means that we were not able to solve it with a single model, okay? But once we have more than one model, then actually we can solve the problem. So in that aspect, it's actually quite interesting. Now the fifth interaction style, which I'm sure you've all heard of it by now, is called virtual reality. The idea is actually very, very old, okay? It goes back to 1968. Mr. Sutherland himself, who was the kind of godfather of graphics, of computer graphics, and a lot of the works that we see, including the mouse, for example, he invented the mouse as well, the computer mouse as well. He proposed it way back in the 1968. Okay. Now the idea here is that we will immerse the user by displaying different images to him through two displays, mini displays placed in front of his eyes. Okay, and I really have some sad news for you here, which is that virtual reality, as much as it sounds cool, as much as it sounds exciting, especially if you tried it in a gaming context or in entertainment purposes, it's actually quite limited. Okay, because this disconnection from the physical world makes you kind of imprisoned in space where you are, because you're always afraid that you will move around and then you will hit something and fall. That's number one. So it has limited success as a general purpose interface. Okay, it is not a general purpose interface. You cannot use it for extended period of time because you cannot basically move. Okay, and this disconnection from the physical world, this continuous disconnection from the physical world, makes it not as interesting for extended usage of time. Now, I also have another piece of news, which is that if you actually use it a lot, you might get tired, and you should definitely try out use it a lot to believe me. The issue is we are creating a 3D illusion or a 3D space that is an illusion, and you believe that you are actually, through your eyes, are seeing a 3D space. But that 3D space is projected on a 2D plane. So it is not true 3D. There is nothing here that is true. It is fake 3D. Basically 3D graphics on 2D. Okay? Or even, if you would like, if you have recorded a movie with 2 cameras, you would think that you capture something that is not computer graphics. Yeah, it's real life captured by 2 cameras, and you're rendering a picture to each one of the eyes, so you get the 3D illusion. But again, the plane of vision here or the vision here, or the display here, is a plane. It's 2D, it's not 3D. And as you keep using it, the brain realizes that, and you already realize that because you know you're wearing virtual reality goggles. So if you actually use it for an extended period of time, you will feel you get tired, and you feel that you're not feeling comfortable. Okay, and this has been known since the early days of virtual reality, that there is a problem that is not really true 3D. Okay, I will not really go into the vision part here, but there is actually a theoretical explanation for this irritation or discomfort that people get if they use virtual reality goggles for a while, because some of the basic 3D vision properties is missing from the display. Now, a spin-off from virtual reality is augmented virtuality. Now, in virtual reality, the user is immersed in a virtual environment where there is nothing real in the environment. It's all computer 3D shapes that gives the illusion of an entire virtual world. Now, augmented virtuality involves establishing a mapping between the objects that exist in the virtual world and objects that exist in the physical world, and that mapping is done automatically by the software. So imagine I am actually putting on virtual reality goggles, and I'm looking at a vase, and this vase has an equivalent one in the real world, perhaps in the room I'm standing in, or in some other place. When someone moves the vase, the physical vase, I see the virtual vase in my scene being moved. So there is a tie between the virtual and the physical. Once you introduce that element into virtual reality, we don't call it just virtual reality, we call it also augmented virtuality. This is an example that I want you to see of augmented virtuality. Very entertaining scene here. You have 2 users, each one of them is wearing a virtual reality goggles, and you see a set of markers placed on their body to track where they are in the scene. And there is a system that doesn't show up in the image here that is mounted in the ceiling that tracks these markers and consequently know where is every body part. So we would know where is the lady's legs are, where is her arms, and so on. Now, each one of those 2 users is seeing a completely different scene. One of them is fishing in a virtual lake, but he is holding the fishing rod, a physical fishing rod, and that's the gentleman, and the lady is flying a kite. Now, so she is holding the ribbon or the rod, the fishing rod of the guy that the guy is holding, but from the other end. When he moves the fishing rod, she feels that the kite is moving in her scene, and when she moves the kite, he feels that someone is catching at his end of the fishing rod, so as if actually a fish caught his hook. So this type of mixing obviously is kind of two-way between 2 users, but each one of them is experiencing augmented virtuality, not just virtual reality. Again, augmented virtuality means at least one object in the scene is controlled via or represents the movement of a physical object, or is controlled via a physical object that is somewhere else, that is being physically manipulated. Obviously, it's hard to build such a system because
you've got to track the physical object in the actual real, physical scene, in the non-virtual scene, and understand where it moved or how it has been modified, and then you change the equivalent virtual object in the virtual scene. Okay? Now, obviously as well, I hope it's clear that augmented virtuality will not work the other way around unless you build a very complex system. I mean by that, if you actually push the virtual vase in the virtual scene, the physical vase is not going to move unless somehow you devise a system that actually moves that. Perhaps you use a robot or something, okay? But usually when people talk about augmented virtuality, they are referring to changes that happen in the physical world and gets reflected in the virtual world, and not the other way around. The interesting thing about this research is that they're trying to do both changes, both directions. Okay, the changes happening from the physical to the virtual and the virtual to the physical kind of thing. Okay, by manipulating this fishing rod. Now, the 6 interaction style we have that we could use, and by the way, you could build the whole system with each one of those interaction styles. You can mix them as well, as I mentioned earlier, but you could build a complete system, independent system, using any one of those interaction styles. So you don't have to, again, and I'm repeating this perhaps for the 3rd or 4th time today, you don't have to actually stick to the desktop way of thinking. Okay, for example, here is a new interaction style that is getting a lot of attention these days. It's called augmented reality. Okay, and I'm sure you must have seen it somewhere online on YouTube, or if you've been to any museum abroad, you would see this app that they would give you in a museum. You install it, or you download it on your cell phone, and you go around pointing the cell phone to different artifacts, and you see through the cell phone the artifact, because the image that is captured by the camera is displayed on the screen, so you see actually what you're looking through as if it's a piece of glass, but you also see information displayed about the artifact. Okay, so augmented reality generally is, the augmentation of physical objects with virtual information. Okay, and in order for us to see the virtual information overlaid on the top of the physical object, as I mentioned, what we do is we capture with the camera what we're looking at when we just display it on the screen. Okay, so the interesting thing about it is that this does not suffer from the problem that virtual reality has, which is that you're isolated from the physical world. The thing about virtual reality, when it was first designed, is that there are benefits, to creating virtual worlds. For example, you could train a pilot to fly an airplane in a virtual reality application, which is actually one of the successful applications of virtual reality. So don't take my criticism of virtual reality that it's completely useless. It has some successful applications, okay? But the biggest problem is that you're isolated from the physical environment. So it's difficult for you even to move around, okay? Now, augmented reality tries to solve this problem by overlaying the virtual information. So we're making use of the virtual world, we are making use of the advantages of what the digital world is giving us, but we're keeping the user in the physical world, in the sense that he can see around him, he can move around, he's not going to hit the door, he's not going to hit into the wall beside him, because he can see everything, and whenever he would like to see or use or utilize the virtual world, he points a device, and the device is smart enough to detect what's in front of it and will start displaying information about the item in front of the user and visible in the device camera. Now, interestingly, augmented reality as an idea has been proposed many years back, and this is something that I would like to highlight, which is that a lot of the products you see in the market today is a result of a research effort that was done 20 to 30 years ago. So if you're actually interested in being a pioneer in any market segment, then look at the research work now, because what is actively being researched now could turn to a product in 20 to 30 years. Okay. Now, in different industries, the life cycle of turning a product from research to a product varies. So in software, for example, it's very short. It will just be a matter of few years. Okay. For example, Google's search engine was researched or developed first as a PhD thesis by the founders of Google. Okay. Now, it only took them about 3 years until they launched the company, because software is easier to actually convert to a product. But for physical products that involve building hardware, this is a little bit longer. So I want you to be always interested in research, not just because you're taking a course or it sounds fun to learn this new stuff, but actually because if you're thinking from a business perspective, then 10 years down the road or 15 years down the road, the new products, the new hardware products that will be in the market are actually a result of research that was done earlier. Okay, so this misconception that exists in Egypt that research is disconnected from the real world is just BS. Okay, it's not true. Everything you see around you is a product of research. Okay, it might not be commercially successful. It might not even turn to be a commercial product, but all products you see are actually a result of research. Okay, so out of all the research projects that go on around the world, perhaps 5% of them will turn to be commercial, and perhaps 10% of those will be profitable. Okay, so anyway, going back here to our example, the digital desk. Okay, this is an amazing piece of work. I really want you to see the video and see it from beginning to end. It is amazing what this researcher was doing back in 1991, which is almost 30 years from today's date. Now, the nice thing about it is the complete fluidity between the physical and the virtual. You don't feel actually, or you don't detect, okay, are we now working in the virtual world or in the physical world? What happens in this work, the setup is like this. He has a desk, that's why he called it, the digital desk. This digital desk has physical paper, including a magazine and books and so on. And there is a camera and a projector at the top of the desk, mounted in the ceiling. And when he opens, for example, a magazine, he will use his pen and finger to label a specific paragraph and paste it in a virtual document. How is this happening? The camera at the top is tracking his finger, and when he starts to expand his finger and pen apart from each other, that means selection. So as a photo is taken from what he's selecting and is translated to an image inside the computer memory, and then when he clicks on the virtual document and say paste, the image is pasted inside the document. So it looks like actually that he's moving the physical stuff, the actual stuff, the printed stuff into the virtual world, into the actual document. Okay, it's quite amazing. So I want you to see it, and this is actually what founded AR. What you're seeing there is the first time AR was proposed, and in a complete video from the beginning to end. He's proposing all kinds of interactions that you would do with AR. Okay, so I like to display or show you these videos because usually the pioneers in an area, we need to give them respect. So, and part of giving them respect is to tell about their work. This is the guy who invented actually augmented reality. Okay, just like we have another guy, Bolt, who invented multimodal interaction many years back. Okay, so, and the other thing is, usually the first breakthrough is quite innovative, and as products gets commercial, some of the features will be taken away, or some of the capabilities will not be possible to support by a company because of profitability reasons. So if you look at any AR nowadays, it doesn't do everything that shows up in this video, even though this video was made in 1991. Okay, so it's an interesting exercise in seeing the impact of research many years down the road. Now, there is a spin-off from augmented reality, which is called mixed reality. Okay, mixed reality goes like this. If you look at a real-world object through your cell phone screen or through any device, a tablet as well, and you see the real-world object being augmented with virtual objects that are embedded in the scene in a way to make it naturally fitting in the scene. Okay, so there's a difference between overlaying information on the top of a display on a display and integrating the information or the virtual object in the scene that you're looking at through the phone.
Now, the best example of mixed reality is Pokemon on the Go. This app, when it was released, it caused a sensation on the net, and actually the company turned to $1 billion company within a few months because of the number of downloads.
So why Pokemon Go was so interesting? It's because it's not just augmented reality, it's really mixed reality here. The thing is not about displaying this 3D character of Pokemon on the grass field. It's how the app understood the scene. So if you're looking for a Pokemon, this is really the what you do in the game. Pokemon hides in places, and in order to be able to do that, the app has to be smart enough to detect what's around it. So for example, you open the drawer in a closet, and you're holding the cell phone, you're playing the game, and the character appears suddenly from the drawer, and it jumps from the drawer onto the floor. And then you try to track the character in, say, your bedroom, and then the app detects that this is actually a bed, so the character is made to run under the bed. And this kind of interaction obviously was, quite novel at a commercial scale. The idea has been proposed in research in various forms, but what the app did is that it took a lot of research ideas and made this app that was again sensational, because people have never seen anything like this before. And this is a prime example of mixed reality, where the virtual character that gets displayed, or the virtual information that gets displayed, is actually reacting to the changes in the physical scene, and interacting or positioning themselves in the physical scene in the appropriate way. So for example, the drawer, when the character jumps from the drawer, because that's the only way you can go out from the drawer. And this kind of behavior of a virtual character that is suddenly acting as if it's a real a living thing is what's interesting about mixed reality. Now here is another example from Microsoft. This is more on the side of science fiction, although it is not science fiction. This research work was called holoportation for a reason, because it is coming very close to what we see in science fiction movies like Star Wars and Star Trek and so on, of this concept of teleportation. Now, this is how this works. It's a very complex setup, by the way. It looks in the video that it's so simple and so smooth, but actually behind it there's tons and tons of research work from various areas in computer science. This is what's going on here. The girl is sitting in a room which is different from where the guy is standing. Now, the two rooms are being captured in detail through a scene analysis system that doesn't show up actually here in the scene. Now, when the girl moves, her body with all the details of her clothes is captured, not just as photos, but as a detailed 3D model. This 3D model is inserted in the virtual model that the guy is actually looking at using the virtual reality goggles. When she moves, her model moves in the virtual world that he is seeing. When he is talking to her and she's talking to him, he is seeing her model talking to him as if she's actually standing in front of him. And that's why they have called it, holoportation, which is, trying to mimic the famous teleportation feature that appears in science fiction movies. So I would definitely invite you to watch the video. It's very entertaining, and it opens the way what can you actually do with mixed reality and augmented reality and so on. This has not been done before. Obviously, when you look at the video, you will understand what I'm referring to, and it opens the way for new types of interactions between people, and new types of communication. It's almost like a science fiction movie in many ways, because we have seen this same scene in many science fiction movies where you see a virtual character get rendered, using some hologram, and it interacts with people, as if actually it is standing with them. The only thing is missing is that exerting physical forces, which doesn't even exist in science fiction movies. Exerting physical forces on the items on the in the scene. So it's quite interesting. Now, let's look at the whole spectrum. We have covered augmented reality, we have covered augmented virtuality, we have covered augmented reality, and we have covered mixed reality. So on a spectrum, VR is at the far right end, where everything is virtual. And on the far left, you have reality, you have the real thing, real life. In between the two, there are augmented reality, where you overlay information or 3D models on the top of or in front of physical objects. And in the middle, you have mixed reality, where the virtual objects start reacting and interacting with the physical world in a meaningful way. And but after that, towards the right, is augmented virtuality, where the virtual object is responding to changes in the physical environment, but it doesn't really understand the physical environment. Okay, so there is a continuum there, and each one of the components on this spectrum has its own advantages and disadvantages and proper usages. And this is what I would like to stress on. That virtual reality is still a nice idea, but in limited applications. Okay, augmented reality is very successful, for example, in cell phones, because people can raise their cell phone and start to inspect or see virtual information. Mixed reality is more towards games and enjoyable, interactive, surprising experiences, I would say. And augmented virtuality is a little bit of a twist on VR. Has not been found lots of usages up till now, but it's an interesting idea to work with and explore. Now we'll move to the seventh interaction style, which are emotional agents. Now, in emotional agents, what we do is we're going to create a virtual character, and this virtual character will interact with us as if it's our private secretary. So we go into a human to human dialogue with the virtual character, almost like human to human dialogue, where we ask the virtual character things and the virtual character responds to us. So it is not anymore a computer, it's more of a 3D model talking to us. Okay, the idea has been put around for many years, has been proposed, has been researched. Really, the problem here is the shortcomings of natural language processing, NLP, which is the branch of artificial intelligence that tries to understand human language. By definition, human language is ambiguous. The words could be overloaded. The words alone are not enough. You have to understand the mood and setting and even the tempo of the conversation to understand what is really meant. So it could be a sarcastic comment versus a helpful comment, for example, that you're listening to. And NLP is advancing a lot, but it hasn't reached to the point that we understand fully how a human talks and what does he really mean. So I'm giving you here a video that you need to watch, which was proposed many years back by Apple. It is following a prototyping style called Wizard of Oz. There's nothing real in this video. It's all fake. It's just trying to brainstorm this kind of interaction technique and how beneficial it's going to be to the user if he just talks to his computer instead of typing, using the keyboard or moving the mouse and clicking on icons and so on. So you can imagine going into a dialogue like, for example, I would like to reserve make a reservation in a restaurant for my dinner tonight with, say, my wife. So he responds back, the character, would you like to eat Indian or Chinese? And then you respond back Chinese. So the character will ask you, when are you planning to go? So you say, okay, I'm going to go there by 8 o'clock. So the character goes, okay, let me check and I will get back to you. And then after 5 minutes, after contacting the website for the restaurant, whatever, it tells you, okay, now I made the reservation for you. So this is really what this is going towards. Now, the eighth type of interaction, we've already covered it, which is physiological interaction, which is obtaining a signal from the user brain or the user muscle, and that becomes the input to the digital world, okay? And it could as well be an output to the digital world, from the digital world. So you are basically communicating using signals and electrical signals and vibrations, and not using a keyboard or a mouse or a desktop. What you see in this video, that I have linked here from YouTube, is a user playing a game, a 3D game, by just thinking of the movements, which we have covered before in when we talked about the brain. And what you see on the center, at the bottom of the screen in the center, there are 3 arrows, and this is the P300 in action. So that's a type of an interaction that you could use to drive a whole program. It's not just for getting one input and that's it, okay? It's not just for detecting, for example, which I described before, the mood of the user. You could even do things like even writing a document, but as I mentioned before, P300 was going to be a little bit slow in doing that. So you could derive a whole interaction using brain-computer interface signal. Here is another piece of work I would like to see. This is using something called EMG, electromyography, to capture the signals from the arm and reproduce that to control the software. So again, this is an example of physiological interaction. Now we will go to the ninth interaction style, which is human-robot interaction. Now, this is actually a whole area within HCI. The idea is, let's forget about desktops, let's forget about keyboards and mice. Let's create robots, and we work with robots, okay? So if I would like to author a document, I would switch on my robot and I would tell him, okay, let's author a document, let's write a project. And I would be dictating to him like the content, and he will be storing it, and finally he will email me a PDF, okay? So no more desktops, no more laptops, no more cell phones. You got this robot walking around and you're interacting with. And this obviously has a lot of implications on many areas, including sociology and anthropology and so on, because what we're talking about here, human-like figures that are not humans, okay? They will be able to express emotions, they will be able to move around, they are completely autonomous, and they're supposed to be helping us in our life. And there's all kind of issues, here, ethical issues. For example, in this study that I have linked you the video for, in Japan, they're very big on actually robots because of the aging population. And one of the things they're trying to do is to create human-like robots. So they're not metal and kind of science fiction-like characters, but they're more like what you're seeing here in this image, okay? They have real texture, they have close to natural skin, they open their mouths and talk in a way that is very human-like. And it's interesting that the reaction of people to such characters is still under research, because there is a lot of reservation from a lot of humans when you start to deal with these characters, to accept them as equal or on par, or to go even engage in a discussion with them. Most humans still don't feel comfortable, and they don't look at them as machines that are made to help them. They look at them as aliens coming from the sky, basically. And there's lots of reservations about creating a beautiful looking robot, for example. And this is what this company is trying to do all the time. They will create robot by Japanese beauty or aesthetic standards are physically appealing, okay, and in all their physical form. And usually the interesting thing is you get mixed reactions or opposite reactions, not mixed, opposite reactions from the genders. So male in Japan would typically like how this female robot looked like, while females will not, and females in Japan will like what this male robot like, but males will not, okay? Because by beauty standards, they're supposed to be above average, perhaps towards the end of the spectrum in terms of beauty by the Japanese standard. Okay, so there's lots of issues there that are quite interesting in the study of how do we create robots that looks like human and how to deal with them. Okay, this is another study along the same way. In this research that I have linked you the video for, the researcher goal was to study human behavior when people are meeting together, to teach a robot how to approach a group of humans standing or sitting together, so that the robot could mingle in a socially acceptable way with humans. This is what all human-robot interaction is about. It's not about just telling the robot something like print me this document or make me tea, but the point is how you can actually integrate robots into human society. Okay. So what you will see in the video is that he will describe how do people mingle. Like, let's say, for example, you're standing in the GC platform, and one of your colleagues come and you're standing with another friend. There is a social protocol that happens, and it's very salient and it's subconscious. If you're talking about something that is private, you will face the other person. But if you're talking about something that is not private, you together will be open a little bit, and you can accept others to come and join you in the discussion. That's what the robot is learning, okay? When he can join a discussion and how he introduces himself in the discussion, okay? Now, so there's lots of interesting topics there in human-robot interaction, but I want you to understand that this is a completely different interaction style, because now the computer is inside this thing, okay? There's no more desktops, no more laptops, no more cell phones, it's this thing, okay? And obviously, you know, we can talk a lot about it in terms of, you know, whether this is the best idea or not. Now, here's an example of how far this was going to go in the future. You know, there are a group of researchers who are advocating that robots should have rights, just like human rights. Okay, which is kind of ironic if you think of, you know, that we're in Egypt that we will ask for robot rights. But anyway, so what do I mean by robot rights? That, for example, you should not physically damage the robot. Okay. And you should properly take off your robot. Perhaps you should clean it. I don't know what you really do with a robot besides cleaning it. But I've linked to you here a video for a lady that actually is putting forward this argument that robots will become part of human society. They will become the dominant actually form of computation. Okay, we will have these you know, walking machines that have amazing processing power that we will rely on, and consequently, in the future, there will be no Windows, there will be no Mac, there will be just robots around. Anything you do nowadays on the desktop could be done through a robot, including searching for a topic you would like to write a research paper on, including buying clothes online. You know, you don't need a web browser, you don't need Chrome, you don't need Firefox, you need a robot basically, okay? So she conducted this experiment trying to test people's reaction to how they perceive robots, and she released this robot into the general public, and it was hitchhiking, and it went actually between several countries until it was finally destroyed by someone who believed that this is a silly experiment. So it's quite entertaining. You should watch the video, you know, and see her emotions towards robots, you know, because, you know, she's expressing emotions that I would say should be expressed more towards humans, not robots, but that's my personal opinion. Now, the last interaction style is the tangible interaction, which is generally abbreviated as TUIs. Now, in the tangible interaction, the thinking goes like this. If you look around how we deal with things in the real life, we're always using our two hands. We're not using a mouse and a keyboard. When you're driving your car, you use your two hands, okay? You don't hold a mouse. It's a shift gear. It's not a mouse, okay? So why? Because we are actually made or designed to use our two hands, okay? Now, we feel more comfortable, will always be the argument, if we use our two hands compared to using a mouse and a keyboard. Mice and keyboards are just proxies, you know, intermediary technology to be able to do the input we would like to do. But really, everything else in our life, we don't use mouses and keyboards. We don't use proxies. We use our two hands. If you'd like to open the door, you know, you don't send an instruction to the door to tell it open it, okay, or open yourself. You hold the handle and you open the door. You're using your hands. So the argument for tangible interaction has always been there in the, you know, in HCI, that we should replace what we have with things that we can move physically, okay? And this is going to be more enjoyable. It resembles what we do in real life, okay? So, for example, if you're a graphics designer and you are building a model of something, okay, you build it physically with your hands. You don't go and open Adobe Photoshop or Illustrator or Maya or 3D Max and build a virtual model. You build it physically, and the computer should track what you have built and translate it to a model later on. So this is one of the earliest work that proposed tangible interaction. It's called MetaDesk. It was done in the MIT Media Lab, and the idea is quite simple. They overlaid a map, and instead of having buttons that you click on to zoom in and zoom out in the map, you hold physical widgets that resembles real tools you use to browse through a physical map. For example, what you see here, the user is holding a lens, and this lens is actually what enables you to zoom in the map. So whatever that's inside the lens is zoomed in. Now, how does this work is described in the video. There is a projector at the top, and there's a screen at the bottom, and you can actually, and a camera at the top, you can actually track where the lens is, and you displayed inside the lens a magnified image. So instead of clicking zoom and moving the mouse, now you work with physical objects, or, you know, gadgets, as sometimes they are referred to. This is another example that takes it in even more, you know, interesting cycle, where you actually manipulate physical objects using your two hands that are being tracked by a scanner. So you could be sitting in a room and manipulating a physical object in another room, and the video is quite entertaining and it's well explained. You know, he's using a projector and a camera, and he is seeing the effect of his changes right away on the physical scene in front of him.
So, the takeaway, there are 10 interaction styles: conversational, direct manipulation, gesture-based, multimodal, virtual reality, mixed and augmented reality, emotional agents, physiological, human-robot interaction, and tangible interaction. These are what we covered today. The other takeaway is that in designing a new interface, we can use more than one interaction style. Okay?